Okay, so let's recall that this is the last result we saw, and what this says is of course that V is a finite dimensional vector space over some base field, and W is a subspace of V. So W of course would also be finite dimensional. Then the space W hat, which consists of all, which is in fact the dual space of W, and it consists of all vector space homomorphisms from W into the base field. If the base field is, if the field of scalars is F, then this consists of all such homomorphisms, which are also called linear functionals on W. Similarly, we have V hat, the dual space of V. We proved that W hat is isomorphic to this quotient of V hat by the annihilator of W. So let's recall also briefly what annihilator is. The annihilator of W is by definition the set of those linear functionals in V, that means those elements in the dual space of V such that Wf is equal to 0 for all elements W in W, where Wf of course is the F image of W. That means this A of W consists of those linear functionals on V which annihilate W totally in this sense. Okay, and we have already seen that this is a subspace of the dual space of V, that means V hat, and these things are true. And because of this isomorphism, it turns out that the dimension of this annihilator is the dimension of V minus the dimension of W. Now, a corollary to this is this next result. The annihilator of the annihilator of W is equal to W. Because it's a corollary to this theorem, it has not been again mentioned that we still have this setup, that still W is a subspace of V which is finite dimensional. But there is a problem. Actually, the equation in the corollary literally is not true. Let us see why. See, so A of W is this thing. That means A of W is a subspace of the dual space of V, that is V hat. And hence, you can of course also consider the annihilator of A of W itself. Just like your original W is a subspace of V, this A of W is a subspace of V hat. Now think of V hat in place of V and A of W in place of W. This is a subspace of V hat. So its own annihilator can also be considered, and that is just this thing. So this will be what? This will then be a subspace of the double dual of V, or the second dual of V. Why? Because you see, if your original W is a subspace of V, then A of W becomes a subspace of V hat. So now here A of W is a subspace of V hat. So A of W will be a subspace of the second dual of V. So strictly speaking, this is a subspace of this space, whereas of course W is a subspace of V, and strictly speaking these two things are not actually the same thing. But from a vector space point of view, there is in fact there is no distinction between these two, and we have in fact shown that they are isomorphic. V is isomorphic to its second dual. And we also know what that isomorphism is, which is in fact an invariant isomorphism. Its construction did not involve any chosen basis for V, although we did use the fact that V is finite dimensional, which we have now observed. And what is that isomorphism? Let's just see that, okay, that explicit isomorphism. That isomorphism, of course, is just this. That isomorphism maps a vector in V onto this function TV. What is the definition of TV? TV is that function from V hat into F, which is defined like this. From V hat into F means from the first dual or the ordinary dual of V into the field of scalars. So you take an element from here. What will an element in V hat be? It will be a linear functional on V, F, which itself is a function from V into F, and its TV image is defined to be equal to the F image of V. Note that because V is coming from V, this VF ultimately, due to the nature of F or what it is in fact a field element. And this association it gives us this isomorphism. In fact, we called it, I think, psi. That is, V psi is defined to be equal to TV. So when we are saying that A of W is equal to W, we are actually using this identification. Under this identification, or under our provision of not distinguishing between V and its double dual, W becomes A of W, or more strictly if I say, W becomes isomorphic to A of W. Because you see, A of W is a subspace of this, W is a subspace of this. Under this isomorphism, these two turn out to be isomorphic to each other. And we in fact, of course, we are not going to be that explicit, but we do use this association. So according to our association, what we are doing is this: if you have any vector in V, you can, in place of this vector, also think of this function. So under our isomorphism, this is the identification that we are using. We are not going to distinguish between the vector V and the function TV that arises from that in this way. So under this identification, this equation makes sense. Literally it does not make sense. Literally it's meaningless, but with this isomorphism it is meaningful, and that's what we are going to prove. So let us now see how we can prove this corollary. Shall I keep just this part like this for some time, and let me start the proof here. Okay, so we are now first of all going to see that W is contained in this. In other words, what we are really trying to show is that if we take an element from W, then the corresponding T that element, okay, T suffix that element belongs to A of W. So let's start the proof like that. Let W be an arbitrary element in W. B want to show that TW belongs to the annihilator of the annihilator of W. If we manage to show this, then according to our isomorphism, we can say in that sense W is contained in this as a subset. So now we have to prove this. So for that, what do we need to do? Okay, by the way, let us also see, because we are going to prove this, what is A of W actually. If we explicitly write down what it is, then we get this. It is the set of, I can write F, but still F feels like an element coming from the ordinary dual. So let me just write T. Such that F T is equal to 0 for all F belonging to, what is the subspace now? Now the subspace itself is A of W. Okay, so if we want to prove that TW belongs to this, then TW should satisfy this condition. That's just it. So that means we need to take an arbitrary element F from A of W, apply TW on that F and see what happens, whether we are really getting 0. For any F belonging to the annihilator of W, we have, now that we have seen what this thing is and what we need to do, we can just get rid of this. So what do we have? FTW. But TW is not just any function. TW has a definite definition. So TW, just like this one, this is equal to the F image of W. However, because F belongs to the annihilator of W, this WF would be equal to 0. So we are getting 0, what we wanted to get. This implies that TW actually annihilates A of W. So W is a subspace of A of W. If you still find this containment somewhat difficult to wrap your head around, you just think of it this way. The isomorphic copy of W, this is your V, and this is your double dual V double hat. You have the subspace W here. Now according to our isomorphism, this W will have an image, which in fact is nothing but the psi image of W. Because this is a subspace of V, this will be a subspace of V double hat. This is a subset of V double hat. Okay, after all. And now A of W of course is a subspace of V double hat. We have shown that this W psi is in fact contained in this. So if you really want to be explicit, you should write W psi is a subset of this. But we don't need those things. Okay, we understand what we are doing. So we have this. Now, okay, now we are going to use the previous theorem. Now y theorem, is it 4-3? Yes, 4-3-2. What is the dimension of the annihilator of the annihilator of W? According to the theorem, it's equal to the dimension of V hat minus the dimension of the subspace whose annihilator we are talking about, and that subspace is A of W. But we already know that a finite dimensional vector space is isomorphic to its dual, so dimension of V hat is equal to the dimension of V itself. But we can of course again use our theorem to write in place of this dimension of V minus dimension of W. Now note one thing, that see, in applying such theorems we may easily overlook one fact, that you should start with a finite dimensional vector space V, and then you have to consider a subspace W of that space, and then all these things happen. The first application of this theorem here has not been exactly on V but on V hat, and in place of our subspace W we have this subspace. But is V hat finite dimensional? Yes, it is, because our original V is finite dimensional, and not just that, in fact they have the same dimension. So we can, in fact, our use of theorem 432 is legitimate here. And now you can see that this just simply becomes dimension of W. So not only is W a subspace of this, but they have the same dimension, and that can only happen when they are equal, and that's how we get the equality. Hence A of W is equal to W. So essentially, if we take the annihilator of the annihilator of a subspace, we don't get anything new, we get the original subspace back, and that's the end of the proof. Now theorem 432 has application in solving systems of linear homogeneous equations. The type of system which, despite its simplicity, occurs every now and then in many places. Linear equations. Let me just use some ink. Okay, so we are now going to consider a general such system. consider the following system of course, homogeneous linear equations, we need not mention it once more. We can see that here. A11 x1 plus A12 x2 plus it goes like that, plus A1n xn equal to 0. This is the first one. Then A21 x1 plus A22 x2 plus A2n xn. This is the second one, and there are many such equations, and the last one is this. AM1 x1 plus AM2 x2 plus AMN xn equal to 0, where the Aij are all in F. So what do we see in this system? Due to shortage of space, it looks a little weird, but you can understand that this is one equation, this is another equation, and this is another equation, and we possibly have other intermediate equations. Now the scheme for using these subscripts, of course, you understand this is not 12, this is 1, 2. It indicates the fact that this coefficient A12 is the coefficient of the second variable x2 in the first equation. The equation number comes first, and then the variable number comes. But the variables, there are n variables x1, x2 and like that up to xn. And there are m equations. This is the first one, second one, and so on, the mth one. And where all these coefficients, of course, are coming from some field F. And you understand what a solution to this system of equation is. It's an ordered pair in the space of all n tuples of field elements that simultaneously satisfy all these equations. Okay, and it is also not very difficult to prove that all such solutions in fact form a subspace of Fn known as the solution space of the system. That's because if you have two such solutions, then their sum is also, you can see those things. Okay, the calculations may look lengthy, but they are routine and straightforward. Only the number of components may be large. That's just it. The complexity will not increase. The sum of two such solutions is a solution, and if you multiply a solution by a scalar, that is also a solution. So the solutions form a subspace, and that is the solution space to the system. Now we are interested in this. We want to know how many linearly independent should I have written those things down? No, I have just explained them, what a solution space is, and in fact why all the solutions form a subspace of Fn, of course. Now we want to know how many linearly independent solutions the system has. What it means is that we want to know that in that solution space how many linearly independent vectors or solutions are there, or in other words we just want to know the number of linearly independent elements or the dimension of the solution space. That's what we want to know. Okay, so what shall we do and how shall we apply our theorem 432 here? So let us see. Now you see that fine, so those n tuples will form solutions, but we have these scalars also. Now in fact they are the only things which are given to us, these aij's, so they will somehow play a role here. We don't really know what these xi's are or xj are. Let the n tuples, let the n tuples, which n tuples? The n tuples that are given by these scalars aij. Let the n tuples a1n, a21, a22, a2n and so on, am1, am2, amn. They are vectors in what space? Again in the n tuple space Fn, and they will span a subspace. They will span some subspace, of course. Let the n tuples span the subspace we are going to give this subspace a name. Span the subspace U of Fn. How many n tuples are present here? M number of them. We don't really know whether all of them are linearly independent or not. That we don't know. If they are linearly independent, then the dimension of U would be equal to M. Otherwise, it will be less than M. So in any case, it's less than or equal to M. That we understand. Okay. Now let V1 V2 Vn be the standard basis vectors of our n tuple space Fn. Now from what we have already seen in this section, we know that if we are given a basis for a finite dimensional vector space, then there is a corresponding dual basis for the dual space of that vector space. Let v1 hat, v2 hat, vn hat be the corresponding dual basis of the dual space of our vector space, that means Fn hat. Okay. We ask or okay, let me write it like this. Of course, we are asking who else will ask. Now, if f belongs to this, that means if f is a linear functional on Fn or an element in this dual space, then when do we have f in the annihilator of u? Now, before we become really confused with all these things, let's just see what we are actually doing. So what we now have is this. We have our original space Fn, and we have its dual space Fn hat. Okay. Now, in the original space we have a subspace, we have got a subspace U. What is this subspace U? U is the subspace spanned by these n tuples, which are coming from where? From our original system of equations. So for this n tuple, for this subspace U, we can of course consider the annihilator of U, which itself is a subspace of our dual space. And we are asking, if an arbitrary element f is given here, when will such an element f belong to the annihilator of U? That's what we are asking. Let us see. So let us start with this itself, because that's what we want. Well, but before we in fact start with this, let us write f as a linear combination of the basis elements of this dual space, and that basis is this dual basis. There exists unique scalars x1, x2, xn. See, when we are saying unique scalars x1, x2, we don't mean these scalars to be variable. Okay, they are in fact constant. If we are given f, then for that f, such unique scalars exist, so that f is a linear combination of these basis elements using those unique scalars. Why I am saying this? It's because we have used these symbols to denote the variables in the system of equations. They are there, but these now are some unique values. If you still find it somewhat not okay, you can write y1, y2 also. Okay, but this is how we have it in the text, such that f is this linear combination. Xn Vn hat. Now let f belong to A of u. Then what does it mean? It just simply means that if we take a vector from u and on that vector if we apply f, we are going to get the zero scalar. That's what the definition of AU is. Now since say this basis element or I should not say basis element, but this vector which is one of those vectors that span u is also in u. So on this vector if I apply f, then also I am going to get 0. So we have this 0 equal to a11, a12, a1n. On this I am applying f. Okay, but now I need space. We are discussing vector spaces and we don't have much space. Note that our original interval itself is also a linear combination of the basis vectors, standard basis vectors of Fn. And if we express that as a linear combination, then the input becomes this a11 v1 plus a12 v2 and so on plus a1n vn. On this we are applying f, but we know what f is, so we use that expression x1 v1 hat plus x2 v2 hat plus xn vn hat. Okay, now in the next step, what do we write actually? You see, we are what is it that we are looking at? We are looking at the output of this function when the input is this, and the function itself is a linear combination of some other functions, and we know what this class and this x1 x2 all these products what they really mean. If you look at this space, the dual space, in that dual space in fact we have this additions, this multiplication by scalars, and according to the definitions of those operations, in other words the operations that we have in Fn hat, those operations tell us that this thing is equal to this. And in order to make it more clear, I am putting further brackets plus like that x2 a11 v1 plus a12 v2. We want to be absolutely clear about what we are doing. vn v2 hat and like that xn a11 v1 plus a12 v2 plus I should perhaps okay, we can again write that if we want, plus a1n vn hat. So in this step we have just simply used the meaning of this linear combination, and the input stays just like that. as of now we haven't done anything with the input, we have just simply kept the input. So on the input now these individual dual basis vector functions are going to be applied. But how? What are the definitions of these functions, by the way? This vi hat. Vi hat, you see, we already know what these functions are. We are going to basically apply them on the original basis vectors from which the dual basis has been formed, that is the vj's. And the definition of these functions vi hat tell us this, that when j and I are equal, when j is equal to I, then this is 1, and when j is not equal to I, then this is 0. So when you apply, for example, v1 hat on this, then only one term survives, that is the first one, the others will become 0. And here also that will not just simply happen. Now you see, now another thing will come into play. What is v1 hat? We have in fact written what v1 hat is, but what is it? It is after all a linear transformation or a homomorphism on the vector space Fn. So it will distribute itself over the linear combination. In fact, that comes first, and afterwards this definition comes. So if you really write the things down to the absolute detail, this type of things we should do at least once, okay? But when we later become used to this, then we can be more brief. But the first few times around, we should really write all the things. A12, V2, V1 hat, A1n, Vn, V1 hat. So that is just simply this part. Like that, let me now quickly write the other things. A21, V1, V2 hat plus A22, V2, V2 hat plus A2n, Vn, V2 hat xn, A m1, v1, vn hat plus a m2, v2, vn hat. You should not get confused. These things, I mean, you can see how easy it is to make mistakes here. mn, vn, vn hat. Now I know beforehand what we should get, so if I have made a mistake here, then it will become apparent. But now, having said that the vi hat behaved like that, what are we getting now? You see, this will become 1, the other images become 0. Here this is 0 and all the other images are 0 except this one, which is 1. Here all the first all of these are 0 except this one, the last one, which is 1. I mean the image is 1. So finally we are getting this x1 a11 plus x2 a12 plus xn a1n. But if you recall where we started with 0 and we in fact applied our function f on the n tuple a11, a12, a13 like that up to a1n, and that turns out to be equal to this. So what does this tell us? It tells us that these coefficients x1, x2, x3 up to xn, the n tuple that they form is in fact a solution to the first equation. And just like this, because the other n tuples a21, a22 up to a2n and all the others also belong to U, the vectors, I mean the solution space U, or sorry, it's not the solution space, it's in fact that subspace U which is spanned by these vectors. Since those spanning vectors also belong to U, so they will also be satisfied by this same exercise. Similarly, let me write it at once like this: ai1 x1 plus ai2 x2 plus ain xn equal to 0 for I varying from 2 to m. Hence, this is a solution to our system of linear equations. And conversely, if you start with a solution to our system of linear equations, then you can start from here. This will be equal to 0, and if you follow all the steps back in the backwards direction, you will see that f belongs to a of u. So f being in a of u and the coefficients of f with respect to the dual basis, they being, so I mean they forming a solution to our system of equations, they are in fact equivalent. If f belongs to a of u, then its coefficients in this linear combination form a solution. Conversely, if the coefficients form a solution, then they give rise to a linear functional f on fn that belongs to the annihilator of u. So you can see that this sets up a function between the solution space to our system and the annihilator of u, and in fact this function is not just any function, it's a vector space isomorphism, and that is why a of u in fact is isomorphic to the solution space to our system. So in that sense, a of u itself is the solution space, not literally but in the sense of that isomorphism. So we are now going to write this conclusion. This is solution to. Conversely, if, let me use some other symbols, yn is a solution to our system then the linear functional x1 v1 hat, y1 v1 hat plus y2 v2 hat plus yn vn hat belongs to A of u. This association gives us an isomorphism between A of u and the solution space of our system. This last sentence is in fact something that I have written, or what the author is saying, but you need to actually verify this. Okay, we have just simply shown that there is such an association. You will then have to actually prove that the association gives rise to of course it gives rise to a function. And what is that function? Under that function, this n tuple corresponds to this linear functional. So the association is being set up between fn and fn hat, because these are elements this is an element in fn, and the thing that it corresponds to this thing, or rather this is an element, this y1 y2, this is an element in fn, and it corresponds to this linear functional which is an element in fn hat. But of course not necessarily full fn and full fn hat, but rather only between the, on this side you have the solution space to our system, and on this side you have A of u, and that function in fact is a vector space isomorphism which is onto, and that's why A of u is isomorphic to the solution space of our system. So we are now able to calculate its dimension, and this is where theorem 432 plays its role. Hence, dimension of A of u is equal to, okay, but now we know what this dimension is. But from that theorem, this is equal to the dimension of fn minus the dimension of u. Dimension of fn we already know, it is n, and let me call this dimension r, where r is the dimension of u and r is called, it has a name, the rank of our system. Okay, so for example, let me just take one concrete example. Say we have two equations in three variables, m equations in n variables, m and n can be any positive integers. So say we have two equations in three variables which look like this: x1 minus x2 plus x3 equal to 0, but of course homogeneous equations. That means the right hand side is 0. There is no non-zero constant involved in the equation, constant term. And another equation say is like this: 2x1 minus 2x2 plus 2x3 equal to 0. Of course, you can just simply see that you can tell me, okay, you can just simply cancel 2 from both sides, yes. But this in general it may not be so obvious. However, just for the sake of seeing what we have here from this discussion, actually we have 2 equations and we have 3 variables. Okay. Now, fine, how many equations we have, that is not that important, but we have 3 variables. Now, can we calculate the rank in this case? What is the rank? See, according to the definition of, according to what we have seen so far, what is U? U is the subspace of F3. For the sake of being more concrete, let us just consider the ordered triples of real numbers. Let these be real numbers, the coefficients. Then the rank is the dimension of the subspace spanned by these 2 vectors in R3. One of them is 1, -1, 1, A11, A12, A13, and the other one is 2, -2, 2. So U is the subspace spanned by these 2 vectors, and you can of course see that any one of them is a scalar multiple of the other. So the dimension of U in this case, or rank, is in fact equal to 1, because we do have one non-zero vector that forms a linearly independent set. That means the solution space to this system, whatever it is, will have dimension 1, n minus r, that is 3 minus 1 equal to 2. So it will be a 2-dimensional solution space. And if you really think about it, you can see that if you really go for solving this system of equations, you just neglect this equation. That's because it is arising from the one above it in this simple manner. So you just consider one equation, and that one equation of course can be solved. So to solve this equation itself, what you do, you keep one variable on one side and you take the others to the other side. You can see that you can choose any values for the variable x2 and x3 independent of each other, and once you do that, the third one is then determined accordingly. So you can choose x2 freely and you can choose x3 freely, and x1 gets determined. And the fact that these two can be chosen freely independent of each other in fact gives rise to this dimension 2. So the solution space is 2-dimensional, but the rank is 1, and there are 3 unknowns, 3 variables. And this whole thing in fact it has in fact been written as a theorem itself, and the general thing, the theorem is this, which is just simply a summary of what we have seen. If the system of homogeneous linear equations, which of course is what we have already seen, a11 x1 plus a1 and xn equal to 0, and there are possibly others, and there is a last one. Keep in mind that in any such system there can be any number of equations and any number of variables, and that any number in each case is of course at least 1. Mn xn is equal to 0, where of course these coefficients are coming from some field f. If it has a rank r, if it is a rank r, then the dimension of the solution is, or we can say it like this, like how the author has said, then there are n minus r linearly independent solutions to the system. N minus r linear. Why do we actually need to know how many linearly independent solutions there are? That's because if we find them, then they are necessary and sufficient to generate the whole solution space, because they will form a basis of the solution space. And there is a very useful corollary to this theorem, and that corollary is this: if n is greater than m, then a system of linear homogeneous equations, but a system of, let me put it here itself, m linear homogeneous equations in n unknowns or n variables has a solution x1, x2, xn, where not all the xi are equal to 0. Such a solution where not all the xi's are 0 is called a non-trivial solution. You may have noticed one thing, or you of course maybe already you know it, that any such homogeneous system, due to the fact that the right hand sides are all equal to 0, the 0 tuple of course is always a solution. Now it may happen that that is the only solution to a homogeneous system, but there may be others, and when the number of variables is greater than the number of equations, then there is at least one other, at least a non-trivial solution where not all the components are 0. There are non-zero components also. But why? And the answer it depends on this previous theorem. Let me just briefly write why. You see, so we now have a system of, again, a system of m linear homogeneous equations in n unknowns. So we know how many linearly independent solutions there are. We know that number, and that number is of course dimension of A of U, because that's how we in fact we established the previous theorem. So this dimension is less than or equal to m, right? Why? Because we have seen that when we have such a system of equations, then what is U? U is still that subspace spanned by those m n tuples that you form out of the coefficients coming from the system of equations. So dimension of A of U is less than or equal to m. And am I getting it correctly? Yes. And this thing is n minus r. I think I am missing some, maybe I am confusing some parts here. Dimension of this, okay. No, what the hell have I written? Yeah, that's why it is so confusing. Dimension of U is less than or equal to m, because U is being spanned by those m vectors, so its own dimension cannot exceed m. And this U, dimension of U, is in fact the rank of the system. So rank is less than or equal to m. Yeah, now it will come, and it is given that m is less than n. So that means that r is strictly less than n, or this. That means this is the dimension of, yes, this is the dimension of A of U, which is equal to the dimension of the solution space also, and that is a positive integer. So it's not zero dimensional. In the solution space there will be at least one non-zero vector, because the only zero dimensional subspace is the trivial space consisting of only the zero vector. So that means there will be something other than the zero vector in the solution space, and that such thing will give you one such non-trivial solution. So finally you have this result. Just simply, if the number of variables becomes more than the number of equations, at least one non-trivial solution exists. It must exist. And here this section ends. In the next vector space update, we are of course going to next solve the exercises, and then we will move on to inner product spaces. So with that, I end this video here itself, and the next update is on Friday, and on Friday let's do calculus again, and then we will go to graph theory. So that's just it. So see you on Friday with calculus. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.